Hi guys, can you hear me? Okay, cool. So who had fun on the midterm? Some people, that's good. Okay, well, it's gone, right? So you cannot change it. That's good. So we get to another part of the course. Can you hear me? Because somehow I don't feel like it's really. Can you hear me all right? No. I'm just trying to move this. Can you hear me now? Yes, okay, now it's better. All right, now we start another a few sequence of lectures that actually have to do more with a subject that I love and actually I work in. It's called complexity theory, okay? So it's only a small number of lectures. If you're interested more in this subject, sometimes we offer a course, I think it's CS172, I think. Yeah, computability and complexity. It's not offered very often, unfortunately, because a lot of our resources are drawn into courses like these that require 2 faculty every semester to teach, right? But whenever CS172 is offered, it's a great course to learn more about computability and complexity. So let me try to frame the discussion today via an example. So we're going to look at, again, a problem, okay? But then we're going to try to abstract away and see kind of what's going on. How many of you have seen in homeworks or discussion sections how to solve bipartite matching using max flows? All right, not too many. That's great because we're going over that now. So we'll start out with just talking about yet another reasonable question to solve, but then I'll try to point out some things and try to highlight some patterns that have been happening all semester, and sort of pointing out these patterns is kind of the job of complexity theory and trying to kind of go a layer above algorithms, right? It's kind of algorithms about algorithms, okay? So let's start like usual. Let's talk about a problem. So we're going to talk about the problem of bipartite matching. Okay, so the input is going to be a bipartite graph. So what is a bipartite graph? It's a graph that has 2 parts, right? That's what it says. So what are these 2 parts? It means that you're going to take the edge set, the vertex set, and think of the vertex set as made up of left vertices and right vertices. So here they are. Okay, so this is every vertex is either on the left or on the right. Okay, and then you have an edge set that connects them. Okay, so it only connects a left to a right, but not 2 left vertices or 2 right vertices. So that's your input. Okay, and the output, what you want to do is you want to output a matching. And syntactically, a matching is just a subset of edges, okay? That satisfies a certain property. So it's a subset of edges such that what? What do you think is a matching in this case? Yeah? Right, so every vertex participates in at most 1 edge. Another way to think about it is that just edges don't collide, right? So they don't share endpoints, okay? Edges do not share endpoints. So it means that basically you're selecting some vertices to be part of the matching, but every vertex can only be matched in a particular way, okay? It cannot be matched sort of in multiple ways. And the goal is want to maximize the size of the matching, okay? So in the bipartite matching problem, we have a bipartite graph. We want to find the matching of largest size, okay? So where would this type of problems show up? Like, why is it a natural problem to study? Yeah? Excuse me? Yeah, sure, but I guess dating websites, you don't have like a global algorithm that is sort of some demagogue that is sort of matching everybody. Normally you choose, right? And also especially these days, in the Western Hemisphere, Berkeley too, this issue of edges do not share endpoints seems to be like a stretch, right? So it's okay. But maybe more concretely, maybe you have multiple processors, right? And maybe you're assigning tasks to it, right? And every processor can only handle a task at any given moment in time, and so you kind of want to sort of optimally allocate these things, right? So whenever you have, people and tasks, or I don't know, you have a schedule and you sort of put in things inside the schedule, whatever, right? So is wherever something cannot be doing something, whenever you have something that is doing one task but cannot be doing two tasks at the same time. All right, so pictorially, typically what you want to have in mind is this picture, right? You have sort of things sitting on the left, things sitting on the right, and maybe they don't even need to be the same number, right? Maybe there is 4 left there are 4 left vertices and 5 right vertices, okay? And your edge set could be doing all kinds of things, right? Notice that it's always between left and right. You don't have edges between lefts and between rights, right? And kind of you want to pick out, so and this person is useless, so it's not so you want to pick out a subset of edges that maximizes its size as a matching. So for example, if you were to pick this edge, that already excludes this other edge as being part of the matching, because then these two edges would share an endpoint, okay? So I could, continue and say, okay, is this on a matching, these two edges? Yes. Is it a maximum matching? No, because, for example, I could throw in this one as well, right? So is this on a maximum matching? Yeah. Well, how can I prove it to myself? Well, I have 4 things on the right. One of them has no edges, poor guy, right? Each one of the other vertices is matched with at least and at most one person, right, on the other side. So clearly this one cannot be beaten, right? So this is an example of a matching that is maximal, okay? By the way, I will keep interchangeably saying maximum and maximal. They actually usually mean different things. I forget which one means what, but one interpretation is that take a matching that cannot be extended, okay? That is kind of as is, you cannot throw in additional edges. Doesn't mean that it is the one of largest size, because maybe you should have started out in a different way, and other choices would have led to an even bigger matching. It's just the one you have at hand cannot be extended, okay? So right now we're discussing the absolute largest matching, okay? Sometimes we may even talk about the other one. Again, I forget which one means what. Just remember they're different notions, okay? So now we want really the largest matching possible, okay? All right, so, and obviously the question is that when you draw things, you can eyeball them, but when things are big and sort of written in code, you want to have an algorithm, right, to do it. The question will be kind of how to solve the problems. Actually, I will need this in a moment. And by now, right, when you ask yourself this question, then sort of you open up your bag of tools and you say, well, could it be a linear program? Could it be like a recursive, divide and conquer? Could it be a greedy algorithm, right? Maybe it's reasonable, just throw in edges until you get stuck, right? Or maybe do a dynamic programming solution, okay? And here we could get lost, for a while thinking about what to do, okay? Today specifically, I don't want to dwell too much on what's exactly the right creative process to land at a solution. I just want to highlight a solution that does work, because it will then point to some things that we talk about today. By the way, does anybody know what's the canonical solution to this problem? How do you do it? Yeah. Yeah, we frame it as a max flow problem. Excellent. So we try to recycle a problem that we already know how to solve in polynomial time, okay? Right now, we're not exactly concerned about sort of how fast it is, just as long as it is efficient. So we just try to reduce it to something that we already know it's efficient, okay? So at least for today, kind of the answer is going to be just reduce the bipartite matching problem to max flow. Okay, and this kind of word will be very important for today and the next few lectures. What does reduce mean? It means that we take an instance that is given to us, and we try to build an input to a max flow solver that the solver would be able to understand in such a way that if the solver gives us a solution, then we can actually distill from it a solution to our original problem. Now, on the surface, this problem seems to have nothing to do with flows. Where are the flows, right? We don't even have capacities, right? So kind of, you're given an apple, right? So, oh, like, you know, paint it as an orange, right? So there are different things, right? So I could, of course, discard this one and just create a max flow instance and solve it, right? But it doesn't help me necessarily to solve this problem, right? So we somehow need to shoehorn this problem into a max flow instance, okay? This is kind of the essence of reductions, okay? Is it clear, kind of? All right. So it turns out actually reducing it to a max flow problem is not hard at all. So here's an idea. So we're going to take what is given to us and actually augment it, pre-process it, okay? We're going to introduce a source vertex that sits left to left, okay? It's like out to the left. It's neither part of this column nor part of this column, just kind of on its own, okay? This is going to be the source vertex for our max flow problem. Now, on his own, he's not a very interesting guy, right? So he has to start interacting with the rest of the instance, right? So here's how we're going to make it interact. We're going to add edges to each of the left vertices. Okay? So that's how, yeah? Yeah. So right now, we're going to have to start talking. So far, that's another sort of, you have to keep in mind all these syntactic considerations. The problem that is given to us was actually undirected. And now, we're going to use as a subroutine some problem that actually understands directed graphs, right? Because in a network, you know, with capacities, typically you say, oh, push flow in this direction, right? So here it says add edges. What capacity? I don't know, let's put 1 for now. All right. Now, the middle part here was undirected. It also didn't have any capacities. So intuitively, what we're trying to get at is to say, look, if I can push a lot of flow from left to right, maybe it will help me identify the matching, right? Because if you think about the larger the matching is, maybe that helps more flow move from left to right, okay? So let's put our sink vertex on the other side connected to all of the right vertices, right? Maybe also give them capacity 1. And now, in between, it seems reasonable that we should direct all these things. And what do you think is the capacity that we should put? We have to put capacities everywhere. 1? OK, let's put 1. I agree, by the way. Why is 1 a good choice? Why would that 1 be a good choice? Yeah? Sure, like just by symmetry, right? Sort of, look, we're looking at the size of the matching, right? We should really try to treat edges fairly, like they all count the same, right? So that's a reasonable place to start. But that tells us only that the capacities here should all be the same. Why don't I just put 10, 10, 10, 10, 10, 10? That also satisfies that requirement. 1 here is special. It actually equals 1 here. Why is 1 special? Yeah? I can split flows, okay? I mean, flows can be split. But that is going in the right direction in the sense that I'm trying to pick up an edge, right? So if I have a unit of flow here, what could I do with it? Well, I could just send one unit of flow somewhere. That would be kind of like picking an edge in the matching, right? Or worse, maybe I end up sending half in one, half in the other, and then it's unclear what I should be doing with the matching. But we'll get to that in a moment. Intuitively, what we're trying to say is that, look, here's a budget of one choice to you. Figure it out. Okay? It says, here's a budget of one. Figure it out. Actually, here, maybe I should have everything connected. Otherwise, this poor guy. There we go. So clearly, right, so if there are isolated vertices, discard them first and don't talk about them, right? So this is basically saying each of the left vertices have a budget of one, which in an ideal world, we would like them to expand on a single edge, right? Not distribute the flow around, okay? Now, on the other side, we have a similar constraint. Since we're pulling out one unit of flow, right, we would like this person to kind of accept one unit of flow from a single edge, okay? So kind of this one and this one is basically trying to tell us, did you pick this guy in the matching, or did you pick this guy in the matching or not, okay? There's this issue about units we'll discuss in a moment, okay? But intuitively, what we have done is we started with an undirected bipartite graph, and now suddenly we have a network with capacities on it, right? Syntactically, it's a different thing, right? Now, is this guy also by himself? Okay. All right. So say that we run the iterative max flow algorithm on this network, okay? We have integer capacities. What do we know that happens when we run the iterative algorithm with the residual network and everything? Since we start with integer capacities, what do we expect to happen? Yeah. Yeah, well, in principle, my algorithm could say, well, let's put a third here and see what happens. Let's put a fourth over here and see what happens. The particular algorithm that we have, the one that reasons by finding ST paths in the residual network, will always stick with integral flows, right? Because we start with a zero flow. It will look for some ST path. It will look whatever it can push on an ST path. It will be 1, right? Add to it to the whatever flow it has so far, and then repeat. So we keep adding sort of new paths, ST paths. And what happens at each of these iterations is that what we're doing is we're selecting a new edge, right? Maybe we reverse some flows at some point, and then we're just dropping an edge from the matching. But at any moment in time, our flow never has fractional capacities, so not capacities, never carries fractional flow anywhere. Do we agree with that? So at any moment in time, all of these flows, I can map them to a subset of edges. Why? I mean, not why. Which ones? The ones that are selected, that have assigned with flow 1. Okay, so let me write that down. So why can we do this? So the intuition is that the maximum flow will, so actually maybe even be precise, max flow in G prime, which is the graph that we constructed, will use the edges of a maximum matching in G, okay? So we're solving something in G prime, and then we're saying that it will tell us something about G. And another sort of observation is that using, what was it called? I think Ford-Fulkerson, right? The iterative algorithm where you use, I think, use DFS. Using Ford-Fulkerson, we know that all flows that we find are integral, okay? Namely, f of e will be either 0 or 1 for everything, right? Because it cannot be more than 1 because all capacities are 1. So either you're kind of using an edge or you don't, okay? All right. So now we need to convince ourselves formally that this actually makes sense, okay? That as you maximize flow, you are at the same time maximizing the size of the matching, okay? So are there questions so far? Oh, wait, cool. So let's try to argue correctness of this algorithm. By the way, let me also ask. We find the maximum flow, right? We cannot output the maximum flow, so we have to post-process the solution, right? So how do we take the maximum flow and then extract the matching? Just want to make sure that's sort of clear. Yeah? Yeah, I just output those, okay? Excellent. So the answer is that once I find a maximum flow, the maximum flow will be doing things. In particular, I don't really care what's happening here or what's happening here. In particular, in the middle here, every edge carries a flow of either 0 or 1, the end. I take all of the ones that have 1 assigned to it, and I call those a matching, okay? Now, I need to prove that what I output is indeed a matching, right? So claim the edge set M derived from flow F on G prime is a matching for G, okay? So let's convince ourselves of that. So look, it is definitely an edge set. So for it to not be a matching, either it will have some sort of L collision or an R collision, right? That's the only way it cannot be a matching, right? And it's certainly an edge set, right? So it's not like I'm outputting a cat, right? So I'm outputting a set of edges, right? So let's say that it has, by way of contradiction, an L collision, okay? Namely, somewhere, it was the case that I had sort of S, was sending, 1 unit here, and then both of these, so this is kind of in L, and this is R, right? So suppose for a moment that both of these things carry unit 1. Why unit of 1? Because I selected both, right? And I was unfortunate, I got an L collision, right? So I got a collision in L. Yeah. So is this fine? Could it have happened? No, why? Because, yeah, out comes, so in comes 1, out comes 2. This is not a valid flow. It could have happened, right? So an edge collision makes no sense. It can never be the case that I selected as part of my edge set M both these two edges that come from the same left vertex, because that would mean that I'm pulling out 2 units of flow, but really every vertex receives only 1 unit of flow, so that would violate the constraint, so this could not have happened, right? So let's look at the other case, an R collision. Now it's kind of the opposite, right? So I selected 2 edges as part of my matching, and I got a collision on the right, right? And for similar reasons, this makes no sense, right? It could not have happened. When I took edges out of the flow, namely the ones that carry 1 unit, it could not have been that 2 edges both carried a unit to the same right vertex. Why? Because that means that this vertex received 2 units of flow total and only has 1 pulled out. This violates the conservation of flow. Okay? So there's a contradiction. There's a contradiction. This is basically saying that anytime I have an integral flow whether it's maximal or not doesn't matter. At any time I have an integral flow on that network, I can extract from it a matching. Okay? And this is actually a bijection, right? Every time I have a matching, I can construct a flow for it, right? So again, talking about correctness of the algorithm, what we learn is observation that we have a sort of a correspondence between matchings on G are in correspondence with flows or integral flows on G prime. Do you agree with this? Right now we just said that if you give me a valid flow, I'll take a matching out of it, right? But clearly if you give me a matching, I can also pass a flow, right? Which flow should I pick? Right, I just take whatever edges are in the matching, and I just connect, I pass one unit of flow to it from S, right? And from that into to T, right? And I will never violate anything because, right, so if I have a matching here, for example, that's a matching, this one here. That's a matching for this thing, and I say, I want to construct a flow for it. Okay, sure, pass this a unit, pass there 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 a unit. That's an integral flow on the network, right? So matchings and integral flows are kind of the same thing, okay? Now, this doesn't mean that our algorithm is correct, because our algorithm wanted the maximum matching, right? And our subroutine gives us the maximum flow. So now we need to establish that as I increase the flow, so is the size of my matching also increasing, right? Because I want this to be the case. Now, let's look at the value of a flow on G prime. And let's compare to it the size of its corresponding matching. How do these two numbers compare? They are exactly the same, right? So it's true for every flow, right? Matchings M and flows F on G, right? For any matching, if I take the flow corresponding to it, the value of the flow will be precisely the size of the matching. That's why we picked 1 rather than 10, right? Because then it would mean that M equals 10 times the value, or the other way around, one of the two, right? So because for every vertex in the matching, I am passing 1 unit of flow. Conversely, if you do give me an integral flow, right, it will pick some edges, right? And every edge that is picked, that will contribute 1 to the size of M. Okay? So I claim that at this point we're done. Can anybody give an explanation for why the algorithm is correct? Just to summarize what we did. Yeah. Right, so we need to convince ourselves that whatever we are outputting is a matching. We have convinced ourselves of that. And is a matching such that there is no bigger matching. Why would that be the case? Because if there were, then we could construct a flow from it that would be even higher than the one that we already output, not that we already received from the subroutine, right? So it means that whatever matching we obtained is the correct one, okay? I see some people confused. Yeah.
I guess what I'm confused about is why the edges from L to R have to be of size 1. Like if you made them size 2, the flow would still be the same.
You mean, but I would need to put 2 here, 2 here, and 2 here.
No, just in the middle. Like if you made all the middle edges. From the L to the R.
Ah, okay, these guys, yeah, like anything above 1.
Yeah, it would be the same flow.
I think anything above 1 is fine, yeah. No, but it matters, though, that, how do you say, that these guys are exactly 1, because the comparison here otherwise would get kind of a different exchange rate, right? It would still mean a case that we're optimizing overall, right? Because it just changes the units. Okay, So why did we talk about, so also should talk about the running time. So just to close it up, it's not very important. Remember that Fulkerson was not quite polynomial time, right? It was weakly polynomial time. Why? Yeah? Right, I run in time that is linear in the actual value of the maximum flow, right? So I could have to iterate many, many times, right? So here I need to make sure that in this particular instance, running Ford-Fulkerson is fine, right? So what it costs us is that we have the number of edges times the value of the max value of the flow, right? So that's roughly the running time of Ford-Fulkerson, right? So this is the number of times we have to increment, right? And in each time, we have to do this much work to find the path, right? And in general, the value of the maximum flow could be enormous. It could be exponential in our input size, right? But here, we should really measure relative to the particular instance that we've constructed, right? How many edges do we have as a function of our original input? Right? We have to come back here. This is our measure efficiency, our original input, right? So let's say that I have at most, I don't know, n vertices. I have n vertices somehow split between these two, okay? And I have m edges to begin with, okay? In terms of those numbers, what are the number of edges now? Excuse me? N plus m, right? Why? Because look, then we're counting all the edges we had already. That's m. We added new edges. We should count them too, right? 1, 2, 3, 4, blah, blah, blah. There's one per vertex, right? So how many vertices do we have? N. OK. So that's OK. Notice that would have been troublesome if we added an exponential number of edges, right? It means that our reduction would not have been very efficient, right? OK, but that is only one term. This is n plus m. What is the value of the maximum flow? Could it be very large on this type of networks? Yeah? It's bound by number of edges. In fact, it's in a better bound. Yeah, the number of nodes, right? So certainly, I can never pull through this network more than n units of flow, right? Because I have one here, one here, one here, one here. I have at most n vertices anyways, right? So the maximum value of the flow cannot be larger than n. So for this type of network, the max flow, whatever it is, which actually happens to be the size of largest matching, is not too big. OK, so it's totally fine to run Fulkerson, and it will give you a really polynomial time, not weakly polynomial time. It will give you an actual polynomial time solution that is n times m. OK? Why? Because we know the flow is small. OK, by construction. OK. So why did we talk about this today? I mean, first, it's a cute construction where you can use flows to solve a non-flow problem. But that's kind of the theme of what we want to do the rest of today and for the next few lectures. We're going to talk about this notion of reductions, OK? That sometimes a computational task is what we call expressive. It can be used to solve other problems. In this case, max flow was kind of flexible and expressive enough for us to kind of program into it the task of maximizing matchings, right? They're different, but you can bridge the gap between the two via suitable It's kind of programming. You're kind of programming an instance of max flow to do your bidding, right? What you wanted was to find a kind of a maximum matching, right? But that's not max flow does usually, but that's okay, right? You just construct an instance where the process of maximizing flow is whatever you wanted, okay? And this is a general phenomenon that is very important in computer science. And I want to talk about sort of reductions in more generally, okay? To kind of highlight these things. So we're going to say that a problem A reduces to another problem B okay, if any subroutine for B can be used to solve A. So make sure I got my directions right. Yes, because I will always like mess up the directions of this thing. Okay. In this language, for example, what did we just do? We reduced one problem to another. Which problem did we reduce to which one? Yeah.
Reduced finding like the optimal bipartite matching to solving for the optimal flow.
Good. So this is the example. We have learned that bipartite matching reduces to max flow. This is basically saying that you could go ahead and solve bipartite matching any way you want. A particular way to do it is to say, I give you a subroutine for max flow, and then this reduction says that you're done. We don't care how this subroutine for max flow works. It's literally a black box. We are not assuming anything about it. Maybe it doesn't even exist for all we know. We're just doing a thought experiment. In fact, we'll be doing that in next lecture, okay? But the point is we are just establishing a relation between two problems. To say if you could solve one, in this case, max flow, turns out we can solve it, but that's besides the point. We didn't use that fact logically. Then you can actually solve the problem of bipartite matching, okay? So the picture you should have in mind is the following. You have your instance X, sort of, that you want to solve of the problem A, right? And you kind of stick it through a box that is going to pre-process it. Why does it need to be pre-processed? Because out will come some other instance for the algorithm for the problem B, right? So B potentially understands different things than A does. So A will accept certain inputs. B will accept different types of inputs, and therefore we need to somehow program Y, kind of with X in its heart, right? Sort of Y carries X somewhere for us, right? That's what we did here. We took a instance X of bipartite matching, and we didn't literally give it to the max flow subroutine. It wouldn't know what to do, right? It would just segfault, right? Instead, we kind of augmented it. We did something, so that after the subroutine returns an answer, B of Y, we can interpret this answer with a post process, right? Because this is an answer. This is an answer to the B problem. Maybe it means nothing as an answer to the A problem. That's indeed the case here. The max flow subroutine gives us a flow. What good is it for us if we need to output a matching? They're different things. Doesn't mean anything to output a flow instead of a matching, right? We have to take the flow, interpret it. How are we going to interpret it? Well, how we interpret it is going to really depend on the pre-processing that we've done. Because we have set up the max flow instance in this way. Therefore, once we get back the answer, we know how to interpret it, right? By just picking out the edges, right? And then this one kind of gives us the answer on X, okay? Now, so this is the instance of B. This is the solution, sort of to B. And it's a solution for A. This is the final solution. Now here's a question, okay? What is a reduction syntactically? I've put down several boxes, okay? I claim that a reduction is not all of these boxes, only some of them. Reduction from A to B is blank. What is it syntactically? When you want to understand something, it's always important to understand syntax, okay? What is it? Yeah? Yeah, exactly. So that's two algorithms, one to pre-process and the other to post-process. The end. That's what a reduction is, okay? Is a tuple where you have a pre-process algorithm and a post-process algorithm. Okay? Such that when you write them in this fashion with any algorithm for B in the middle, you get an algorithm for A. Okay? You are not, when you look for a reduction, you should not be at all interested. In fact, you should be disinterested on what is going inside here. That's not your job. When you reduce a problem from a problem A to B, all you have to do is to architect, design, how to pre-process and post-process, because you're just doing a thought experiment. You're saying, if I had a subroutine for the algorithm, for the problem B, usually you do, that's why you're doing it, but it doesn't matter. Then this is how you would pre-process and post-process your instance. That's why a reduction is a pair of algorithms, the pre-process algorithm and the post-process algorithm. Usually, the pre-process is the more interesting one, right? By the time you've done this, you know how to interpret the answer, right? So, but it is a design question for these two algorithms, okay? Syntactically, that's what's happening, okay? Now, whenever you have a reduction from A to B, you learn two things. So let me go back up there. And I want to move this example here. So I'm going to say example. Okay, I've just moved the example down there, and I want to use the other side of the board. So if you know that A reduces to B, then you can draw conclusions, okay? So let me sort of spell them out. But anyway, how do you know that A reduces to B? Is because you've constructed these two algorithms, okay? Now, the first kind of straightforward conclusion is kind of a positive conclusion that says that if you find an algorithm for B, then you have an algorithm for A, right? I mean, that's what this chain says. Notice that this is separate. This is like when you actually find an algorithm, then you have a full algorithm, okay? So this is a way kind of to make algorithms when you're lucky later, you know, of all these empty boxes, right? So far, this is you establish a relation, and then later, given this relation, you can instantiate, right? You can literally put in an algorithm. More subtle conclusion is a negative one, which is used most often in complexity theory, because when we quickly move and study problems beyond efficiently retractable ones, all we can do is establish relations. So we're not actually talking about algorithms that we have. So the negative thing is, what is kind of the other conclusion that I can draw from this? Yeah? Yeah, so another way to put it is that if I believe that A doesn't have an algorithm, then B shouldn't either, okay? Because if it did, then A would have it, right? So this is what the reduction tells us, right? So if I believe that A has no algorithm, neither does B. So namely, I don't have to standalone individually spend a lot of time trying to convince, yeah?
Isn't it not true that by that definition that by matching reduces the max flow? Because if we relied on the fact that the workload is infinitely times either way to the axis, so or infinitely for flows, it doesn't we could have an instance where we had a max flow that had non-integer.
Yeah, but we constructed, the question was basically what's up with fractions, okay? It's that we constructed our max flow instance such that first, all capacities are integral by design. We wrote there was no max flow instance. We created it. And we put 1 everywhere, right? And then we specifically ran an algorithm for the Fulkerson that has the property that if you run it on networks where capacities are integral, then all of the intermediate flows, including the max flow that is eventually output, are also integral.
Yes, we couldn't. So we constructed an instance that could have, if there are possible max, there are instances which have max flows that aren't necessarily using all integer flows. Because we can have one and then go to
Oh yeah, so here I need to sort of talk about max flow star or whatever, right? So good point. Yeah. Yeah, and also more generally, it is, so here we were focusing on the sort of intermediate flows, but it is generally the case that with integral capacities, I think in general you can actually make sure your max flow is integral, at least with these particular networks. Not in general networks, but in this particular network, it will always be the case that even if you run a solver, it will only find solutions that we can interpret at the end. It doesn't mean that intermediate states, it doesn't carry some stupid flows that we cannot interpret, right? Good point. And we do care about only at the very end, right? So, yeah. So what was I saying? Yeah, I was saying that a reduction is a relation between problems. It's not a solution of any problem. It's just a relation, right? So if we say that A reduces to B, okay, then if for whatever reason we believe that A doesn't have a good algorithm, an efficient algorithm, then B shouldn't either, right? So if we know A very well, and we reduce A to B, suddenly we also know B very well, right? Because kind of all of our pessimism about A carries over for free in one fell swoop, right, into B, even though B has looked completely different, right? So it's very powerful because kind of holding beliefs like, oh, I don't believe something is tractable, it's kind of it's a strong assertion. So you want to be able to kind of use these assertions as an operational way. Reductions make this possible, okay? So reductions is also, you can think about it as, is a big map, basically with arrows between problems, so which problems can be used to solve which other problems, right? And some problems are more foundational or expressive in that they have many arrows going out. They can be used to solve many other problems. Those are kind of core problems. That's sort of, one of them is linear programming, and we're going to prove right now actually it is core. But before I do that, is there a question about reductions? You should really try to internalize this notion because we'll be using it quite a lot in the next few lectures. Okay? Again, it's just a pair of algorithms, pre-process and post-process. Yeah? Well, let's check this one, right? So if I believe that A has no algorithm, then let me convince you that I should also believe that B has no algorithm. Why? Because if B had it, then certainly A has it by definition of the reduction. If A is reducible to B, does not mean that B is reducible to A. So the other way around would have required me to reduce B to A, but that's not what we had. We had A is reducible to B. Obviously, if you have both directions, then your belief must carry either direction. But if you just show that A reduces to B, all you have learned so far is that a lack of algorithm for A carries to a lack of algorithm to B, because if you had an algorithm for B, then you would have an algorithm for A. Okay? If you want to learn the opposite, then you should figure out a way to reduce B to A. Right? So get your directions straight. Fortunately, there's only two directions, right? So you can check which one is the correct one. Right? Yeah. Great question. So is it possible that a pre-processing and post-processing is a bottleneck? First, we should say that whenever we talk about reductions, both of them should be efficient algorithms, right? Otherwise, consider the pre-process algorithm that says, solve A, do nothing, right, and output the solution to A, right? So what you want to do is you want to bound the power of pre-processing and post-processing in such a way that they're meaningful, right? In general, when we talk about the difference between efficient and inefficient, pre-processing and post-processing can be any efficient procedure. Other times, when we're just trying to make progress in our understanding, pre-process and post-process are just whatever serves our understanding, right? Like, right now, we just related two problems that at the end of the day are efficient: bipartite matching and max flow. So here's a new reduction for bipartite matching. In the pre-process, reduce it to max flow, but don't tell the reduction, right? Just do it inside the pre-processing. Solve it, right? And then, do nothing, right? That's fine, but that's not the point, right? The point was to use the box in the middle to further your understanding. In this case, all we had to do was to restructure the problem, and voila, we're done, right? Like we invoke the max flow subroutine, right? But in general, especially when we talk about interactability, like MP completeness in the next lecture and the one after, you just treat pre-process and post-process as anything you know is efficient, okay? They should not be inefficient, otherwise they don't teach you these things. All right? Okay. All right, so now what I want to do is give an example of a central problem that we can prove sort of is central in the sense that it is some of the hardest of all efficient problems, because all efficient problems reduce to it. Okay, so if you find a problem to which all efficient problems reduce to it, certainly can be no easier than any of them, right? It is kind of the hardest problem of all. Okay? All right, questions about that? Okay, so today we're not going to do any words. I'm going to talk about instead something else. How about some tourist suggestions? Sounds good? Yeah, sounds good. All right. So, but non-standard ones. Otherwise, you can easily find those, right? So. So here's something that I really like. So, so up in the north, where I grew up, it's mostly mountains and lakes. Very nice. And you may be familiar with one particular lake, because there is a lot of US actors that sort of bought nice houses there. What is that lake? Como, exactly, Lake Como. But that's not what I want to talk about, because somebody knew about it, right? So. So the other one is, so lake is lago. Maggiore is lake major. Okay, why? It's big, okay? So it's about 100 kilometers west of Lago di Como. It's sort of split between Switzerland and Italy. And what's notable about it? Well, it's very beautiful. There's a lot of sort of small towns on it, very beautiful. There's mountains in the background. And a particular touristy attraction that is probably more familiar to people in Europe rather than to people living on this part of the world is there's something called the Borromean Islands. It's a group of 3 islands in the lake that can be visited using, you take a boat, you go on a ferry, you go to the island, you go on the island, out of the ferry, right? And you walk around and you kind of go on the other islands. Very beautiful. There's old villas on these islands and with nice sights around. So okay, that is if you want to do sort of the kind of quiet touristy things. Nice things in the north. Actually, there is lots of hiking opportunities. So let me give 2 hiking examples that are nice. One is, actually it's not even in Italy, it's like in Switzerland, but that doesn't really matter, it's the same region. One is Val Verzasca. It's at the top of this lake, okay? It's at the top of this lake. Val is valley, okay? And it's really beautiful. If you're into rafting, there is places to do rafting. And there is, I think, reasonable hiking, meaning that you don't have to plan too much for it. Very beautiful. Another place I really like is west of this lake is the Park of Gran Paradiso. It was actually the first national park in Italy. It was put together by the first king of Italy, Vittorio Emanuele. And this is the name of one of the main peaks there. It's a mountain, and I don't know in feet what it is, many feet, but 4,000 meters. And for the more sporty ones of you, it's actually a very reasonable summit to peak. You can do it in 2 days, and in Europe, you don't have to carry tents because there are these refuges where you can actually get wine, polenta, and all these things, right? So you first hike up to the first hut, right? You sleep there, and then you start the next day in the morning. You summit, you come back down, and then sort of that's just normal hiking, and this is like a really nice sporty hike. You do need to be roped up, but it's not. Again, if you know what you're doing, it's fine. Okay. So there is some suggestions that are not Venice and Rome. Let's talk about reductions. So we're going to prove that everything, not literally everything that is efficient, reduces to linear programming. Okay? It's a pretty strong statement, right? It says everything that is efficient, reduces to linear programming. So there is some way to kind of rewrite your problem so that you can just push it in a linear program. It will solve it for you, and then you get back the answer. Now, we have to somehow formalize everything that is efficient. That's kind of hard, right? Could be problems that we've never met before, and they are efficient, and we have to talk about them too, right? Maybe there are problems that tomorrow we discover they're interesting. We never even formulated them yet, right? So how do you even talk about it? So the way to talk about it is using you talk about computation as in the general sense. So we're going to define first, to talk about that problem, we have to first define the notion of a Boolean circuit. Okay? So a Boolean circuit is a direct acyclic graph, a DAG, okay, of so-called gates. Okay, so, and they have several types. You know, there's going to have an input, they have input gates. And the input gates say that you have either xi equals 0 or xi equals 1. That says, you know, the input, you know, this location is either 0 or 1, okay? You have AND gates. You know, that says that xi times xj, you know, goes to, so xi and, how do I write it? And xj goes to xk, okay? You will have, you know, whatever, OR gates that says xi or xj goes to xk. By the way, what are these gates? This is just saying that there's a node, right? And the node in the graph, you know, kind of tells you what type of gate it is, and it receives wires, right? And, you know, the wires are kind of what you're computing. That's why I'm talking about directed acyclic graph, right? And you have NOT gates, which says that, you know, xi naught goes to xk, okay? And also, you know, so some gates are designated as input, okay? Does this make sense? A Boolean circuit syntactically is just a directed acyclic graph where, you know, maybe the in degree of gates is, you know, either 1 or 2, and every binary gate is labeled either AND or, right? And then the gates that have one thing coming in, you take them to be NOTs, right? And at the end of this DAG, there is the output, okay? Sounds like a reasonable definition of what it means, right? Let's define a problem about Boolean circuits, okay? The circuit value problem, let's denote it CV, okay? Is the problem where you're given a Boolean circuit you have to decide if the output is 1. Okay? So I give you a Boolean circuit. I just basically give you a directed acyclic graph labeled with all these things. And I ask you, you know, is the output 1? And let's assume for a moment that it's just one output for now, okay? This is definitely a computational problem, right? Do you agree? All right. By the way, is this problem efficient? Can you give me an algorithm to solve this problem? How do you solve this problem? So I give you a DAG, right? And I give you rules to compute things at every gate, right? And I ask you, yeah?
Well, it's just like an equation, basically, where like your ANDs are just like a function of your input. So
Yeah, so I just go gate by gate. So I could, for example, sort the DAG in topological order. And I just, you know, very carefully go through and I do bookkeeping and I say, okay, now I have these inputs. That means that this output is this one. I continue like that until I'm done, right? So this is this circuit value problem. CV is efficiently solvable. Okay, cool. So what does it have to do with linear programming? Well, two things. So now, let's move here. I'm going to make a statement, so two statements. One will prove, the other one is just kind of true by philosophy, okay? So claim 1 and claim 2. All right, claim 1 says that if A is efficiently solvable, then A reduces to CV. Okay? And then the second claim is that CV reduces to LP. Okay? Is it clear what I'm saying? I'm saying pick some problem A, and let's say that it is a problem that is efficiently solvable. I don't care what the problem is. Just say it's efficiently solvable. Then I claim that that problem reduces to the circuit value problem. Okay? We'll talk about this in a moment. And the second claim is that the particular problem circuit value, okay, reduces itself to linear programming. And when I chain these two things together, we learn that everything efficiently solvable actually reduces to LP. Okay? So this we'll prove in a moment. I want to convince you this is the case. We don't have the languages in this course to actually prove this formally, but let me try to convince you of that, okay? So what does it mean that an algorithm, there is an efficient algorithm for a problem? It means that at some point, I can write down, like, in Python or in C++ or in assembly even, right? Some sequence of instructions, right? That on every instance spit out the correct answer, for that problem. Now, at some point, you take this program and you say play, right? Now the machine, as you know, is not magical, right? So if you open it up, there isn't an elf inside that doing some magical things. You don't know what's happening. You start, opening it up. At the end of the day, it's just, things flowing in a circuit, right? There are these elementary logical gates that are computing for you. They're very tiny. You cannot see them. That's why computers are fast, because these things are very tiny, right? But at the end of the day, there's a processor that is basically doing those things, okay? It has elementary instructions that says, okay, take this register, add it to this other register, store the output somewhere else, fetch this thing from memory. You have these elementary things, right? So the assertion that an algorithm, a problem has an efficient algorithm is tantamount to the assertion that there is a polynomial size circuit for it. Because if you take what your computer is doing and you unroll it, right, you will get essentially a Boolean circuit that does whatever it was doing, right? It's just you expressed it in higher level languages, right? Now this feels like fluffy. Now, first, it's literally what's happening, right? Okay, there's transistors and things like that. There's not literally logical gates, but once you kind of correct for the analog-digital divide, you are computing digitally, right, on those things, right? Now, formally, mathematically, how do you actually talk about this? Well, in computer science, we don't talk about physical computers formally. We have things called Turing machines, for example, or automata, right? These are things that, I don't know if you've seen in other courses. Certainly, you would see in a computability course. And there are formal mathematical models of computation that tell us what does it mean formally for a problem to be efficiently solvable. And you take those things and you reduce them to circuits, okay? But the physical analogy carries a lot of weight because that's literally what's happening anyways in a computer, right? So anytime you write an algorithm, you have implicitly found a reduction to the circuit value problem. That's what has happened, okay? It's just part of the reduction is automated for you by an engineering stack underneath you, okay? So this is kind of by definition, right? What else does it mean to solve a problem efficiently if not that there is somehow, somewhere, a circuit that is written that kind of embeds inside it your problem, okay? Does it make sense? Again, this can be formally defined. You just need a formal model computation, but we don't have it in this class, so we have to check mark it like this, okay? But the high-level argument makes sense, right? What else does it mean otherwise? I have an efficient algorithm. Okay, it means that you have an efficient algorithm to tell the computer what to do, and the computer is doing those things anyways, right? You just instructed which circuit to write, okay? What is less obvious is what does linear programming have anything to do with computers? This is essentially what it's doing is that a linear program can be used to simulate a computer. This is what this is saying, right? We can take any arbitrary circuit and use a linear program to solve it, right? This we can prove because we have a definition of this one, we have a definition of that one, right? So now this actually we can prove, okay? So we're going to do that now. It's actually pretty easy. So we have to write a linear program, okay? So we need to introduce variables and constraints, right? So for every gate G, introduce a variable x sub g with the constraint that it is between 0 and 1. Okay, that's a linear constraint so far. Okay, now we have as many variables as there are gates. Then, for the input gates, these guys, well, they're already linear, so let's just copy them, right? So for the input gates, introduce the constraint either xi equals 0 or xi equals 1 as needed. It depends, what you had there, right? So for every gate, if it is an input gate, put in the constraint xi equals 0 if that's what the circuit wanted. Otherwise, put xi equals 1 if that's instead what the circuit wanted, if that's what the circuit wanted instead, right? All right, so the input gates are easy. Let's look at AND gates because this doesn't look so linear, does it, right? It doesn't look very linear. We need to somehow design a small gadget that will kind of realize this in some sort of roundabout way, okay? And these gadgets is kind of the tricky part of reductions, that because you're reducing apples to oranges, somewhere you have to figure out, how does an apple relate to an orange, right? And you have these small gadgets that kind of implement this gap. AND gates, so here's a way to do it. You're going to say that xi is, no, xk, sorry. xk is at most xi, that's linear. xk is at most xj, that's not a second constraint, also linear, okay? And then we're going to say that xk is at least xi plus xj minus 1. All right, let's test this. An AND gate has 4 possible combinations of inputs, right? 0, 0, 0, 1, 1, 0, 1, 1, right? And on each of them, we need to get the right answer. So suppose for a moment that both inputs are 0, 0 and 0. That means that xk has no chance to be anything other than 0. Is it consistent with this one? Sure, because it says 0 is at least 0 plus 0 minus 1. Great. So 0 is the only thing that xk can be, and it is consistent with all of its constraints. Let's try 0, 1. Let's say xk is a, which, by the way, the correct answer to 0 and 0, 1 is still 0, right? So here we have 0 is less than or equal to 0. Great. 0 less than or equal to 1. Sure, that's also fine. xk is at least 0 plus 1 minus 1, 0, right? So again, xk is forced to be 0, and all 3 constraints are satisfied. Let's try the last option. I mean, by symmetry, 1, 0 is the same thing. Now we look at 1, 1. 1 is less than or equal to 1, sure. 1 is less than or equal to 1, also sure. 1 is at least 1 plus 1 minus 1, which is 1, right? So the only valid answer for xk, again, is 1, which is the correct thing, okay? So that's gate. That's gate. That's a gate, and that's great. For OR gates, something similar holds. I'm not going to go through it, but I can show you the gadget. xk is at least xi, so I'm kind of flipping things. xk is at least xj, okay? And what's the other one? xk is at most xi plus xj. Okay, so this actually implement OR gates. NOT gates is clear. It's just x goes to 1 minus x. Now, what's happening here? We're just writing constraints that are simulating gates. So start from the top. These values are fixed. And at every gate, these gadgets actually exactly fix the value for the output of the gate. And you just continue like this. Okay, so at the very end, the value of the output gates is just forced. It's forced to precisely what it should have been. So essentially, this linear program is almost degenerate. It has exactly one feasible solution, which is the answer. Okay? Are we convinced? It's almost trivial, right? It says, those are the gates we have. Let's have gadget for each one of them. As long as we can express them as a collection of linear constraints, we're good, right? So what this is saying is that linear programming is expressive enough to encode inside it the hardness of any computation, right? Here's an arbitrary computation encoded inside it, right? So, and we could, even though that's a bit roundabout, to call an LP solver to give us the answer to this circuit. Well, this makes no sense to do it, right? You might as well compute the circuit yourself. This is just demonstrating that that linear programming, in principle, has inside it kind of the generality, expressivity of all problems that are efficiently solvable. Okay? So in this sense, it is a central problem, just like the circuit value problem is a central problem. This property is non-trivial. For example, it is not the case that the problem of multiplying two integers is like this. It is not the case that everything reduces to it. If you can multiply integers, then you can solve everything else. Okay? There are certain problems that are sort of harder than others, okay? Because a lot of things reduce to them. Linear programming is one such thing. Now here, it feels a bit artificial what we're doing, because if you're really paying attention, you could say, well, what does it mean? Like LP is efficient, but so is the pre-processing and the post-processing, right? So what does it really mean? You could have solved your problem in the pre-processing or post-processing phase and then leave no work to LP. That's true, but that's not what I did, okay? So what you always want to have is the pre-processing and post-processing to be weaker than the problem that you're trying to solve, right? So one way to formalize what I just said is you make the pre-processing and post-processing, for example, run in linear time, okay? To the extent that your LP solver runs in more than polynomial time, and you don't have maybe linear time algorithms for CV, which actually we do, doesn't matter right now, then sort of it prevents the pre-process and post-process from solving the problem for you. Either way, because I don't have an adversarial pre-process and post-process, I'm an explicit one. It's clear that we're not solving the problem in the reduction. The LP is solving it for us, right? So in this sense, it reduces, it is as hard as all problems. What we'll do starting from next week is we'll stop looking for 1 or 2 weeks at problems for which we actually have algorithms. We're going to try to use this lens of reductions to map out relations between hard problems, okay? And something similar will happen where there are problems that are hardest of all other problems.